Part 2, Virtual Docking. Now, coming back again to this idea of two surfaces interacting with one another. As I said, there are four components that are involved. Van der Waals interactions, electrostatics and salt bridges. We normally define as a salt bridge as an electrostatic interaction that is also making a hydrogen bond. Hydrogen bonds and hydrophobic bonding in inverted commas. Now, the binding energy, the actual affinity, is largely driven by the hydrophobic effect. However, if any of those other things are mismatched, then it will be less favourable than having them out in the solvent. So while they do not directly contribute very much to the actual binding energy, if there are mismatches, then the binding energy will be badly affected. So we can't have a situation like this in the bottom left where there's a big gap, although sometimes water can fill those sorts of gaps. We can't have a situation like this where we have positive charges interacting with one another. What we're looking for is something like this, where we have good matching of the shapes, good matching of charges, good matching of hydrogen bonds, and the hydrophobic effect, bringing hydrophobic surfaces together. So the docking that we're looking at can be a protein interacting with a small ligand, or with a peptide, or with another protein, or with a nucleotide. But of course what we're mostly interested in from the perspective of drug design is proteins interacting with small ligands. Now, docking in a computer is far from trivial. And one of the main reasons for this is that both molecules are flexible. And that means, as well as positioning the two with respect to one another, there are hundreds of possible degrees of freedom in terms of relevant side chain positions or relevant flexibility within the small molecule that somehow have to be accounted for. And that means that there's an astronomical number of possible conformations. Now, in the case of these protein-ligand interactions, we often treat the protein as rigid. And obviously that's a major simplification, but one thing that we can do to improve on that somewhat is to run a molecular dynamics simulation on the protein, which allows it to move around and allows those flexible side chains to move. And then we can take several snapshots from that dynamics simulation and dock against each of those in turn, treating each one as rigid. So if we just think about simple rigid body docking where we treat both the small molecule and the protein as rigid, then there are 6 degrees of freedom. So there are 3 rotations about X, Y and Z axes and 3 translations along X, Y and Z axes. So this is just like something like docking the space shuttle with a satellite, that sort of interaction. We've just got 2 fixed solid bodies which are completely rigid, and we're moving them into the optimum orientation. As I said, we do often treat the receptor, the protein, as static, but it is much better if we can treat the ligand as flexible. And in that way we can dock a ligand into a binding pocket and generate a large number of possible orientations, both in terms of the conformation of the ligand itself, but also in terms of the orientation that that particular conformation has within the binding site. And then we need to evaluate those by using some sort of energy function. So in this small molecule, typical sort of size drug at the bottom here, we have a total of 9 rotational degrees of freedom about bonds. So we can rotate about this bond, this bond, this one, this one. This one we can't rotate about because it's a peptide type bond, so that's going to be delocalized, and but we can rotate about these other bonds here. Now, There are many programs available for automated docking, and I've just mentioned a few of those at the bottom there. And they take somewhat different approaches. They all make use of cavities, so this idea of finding a pocket that I mentioned previously. And what I've shown on the right is a kind of mesh drawn across a protein with a pocket which is then filled in by a small molecule drug. They all also take into account surface complementarity, so trying to see how well the small molecule fits into the pocket. But they may also make use of things like electrostatics and may include some sort of full energy function. Now, one of the oldest programs, and still a popular one, is called DOC. And the way that this works as a kind of classic basic approach to docking is it starts off by generating a surface, a molecular surface, that we can then use to define the shape of the pocket that we're docking into. So in this case we're looking at the HIV protease as a target receptor. These two red aspartate groups form the active site. So here we have a Connolly molecular surface drawn across that, and that really is our surface onto which we want to dock our small molecules. And the way that DOC works is then to generate spheres to fill the active site. So the cavities are used in order to define where these spheres can go. So if you think of the cavity like some sort of plastic convex shape, then you could drop ping pong balls into that shape and see where they end up. And you could do that several times and they might end up in somewhat different places each time. The centres of each of those ping pong balls then become potential locations for the liganding atoms. Consequently, the next problem becomes, how do we fit our molecule onto those sphere centres? So essentially what we need to do is be able to match those sphere centres against the ligand atoms. And it may be that not all of the ligand atoms are relevant. So this is a kind of graph matching problem and allows us to find possible ligand orientations. And often there will be more than 10,000 orientations possible for a single ligand in a single conformation. So what we're trying to do then is find a transformation, a rotation and a translation in 3 dimensions, so 6 degrees of freedom, which will maximize the matching of spheres. In other words, matching of atoms within our ligand with where those sphere centers were in the protein's pocket. So here on the right we've got a pocket with a set of 5 different spheres, and on the left we have a molecule also with 5 atoms. But in this case, the shapes of those are quite different. However, they have a common feature. They have this triangle of 3 atoms, and you can see that those would map onto those 3 sphere centers on the right. Now, the matching in the pocket on the right may not be perfect. There's a bit of a gap here, but that's something that we can deal with later when we refine a small molecule to get it to fit better into a particular pocket. As I said, we may have 10,000 or more different orientations for a given conformation of a ligand, and therefore we need to score those and find out which is likely to be the best conformation and the best orientation. So DOC provides 3 scoring schemes. The first is a simple shape-based scoring, and that's really just matching where the atoms go into the pocket and the spheres that we have placed within the pocket. The second incorporates electrostatics. It uses a program called Delphi to calculate an electrostatic potential. And the third is a full force field scoring, which uses the AMBER potential. So AMBER is a molecular dynamics and energy minimization program, a bit like other things such as CHARM and GROMACS. It uses the potential, the force field from that, in order to score how well the ligand fits into the binding site. But really the shape complementarity is key. Having protein and ligand surfaces that are complementary to each other is absolutely essential, and we can look at this using a simple kind of geometric descriptor. The other advantage of this, of course, is that it's much faster than these other more complex methods. Evaluation of how good the complementarity is falls into two basic approaches. The first is to use surface curvature or surface areas based on that Connolly surface that we saw before, and calculating a similar sort of surface over the small molecule and seeing how well they match. The second is a kind of grid-based approach where we draw a grid over the interacting region between the small molecule and the protein. And if that grid is fine enough, we can evaluate for each point on the grid whether it's occupied by an atom or whether it's a gap between the two surfaces. And therefore we can evaluate quite easily how good the complementarity is between the two surfaces. Now when we go on to use a full energy potential for scoring the interactions, one problem is that the best binding site orientation is not always the lowest energy. In fact, we find that the true binding site orientation often has a higher energy barrier around it rather than being the lowest overall energy. And the effect then of having this high barrier around a particular binding site is that we need a lot more energy for the molecule to leave that binding site. So if we imagine this is some sort of interaction profile along here, clearly the lowest energy orientation and binding is at this point. However, to escape from that, we only need 10 kilocalories per mole of energy. Whereas this site, which has a higher overall interaction energy, requires 15 kilocalories per mole to leave it. So once we get stuck in this local minimum, we're much less likely to escape. So in this case, this might be the real site, while these were potential other sites, both of which, if we're just looking at energy of the actual conformation, score lower. So things like molecular dynamics can help here. We select a set of low energy conformations, and then we can do dynamics and simulate pulling the molecule out of the binding pocket and see how much energy is needed to get it out. So how well does DOC perform? At the top here we've got the top scoring orientation for thioketal molecule docked into HIV-1 protease again. So again in red here you can see the two active site aspartates. This is using a force field scoring. And if we compare it with the crystal structure, this is two slightly different orientations of the molecule, you can see really that the orientation is almost perfect. Now DOC effectively uses a rigid body approach to docking. We can generate several different conformations of the ligand and see how well each of those docks using the DOC algorithm. Gold, on the other hand, is a flexible genetic algorithm-based docking method which actually simulates the flexibility of the ligand as it docks it into the pocket. So here we're seeing an inhibitor docked into dihydrofolate reductase using a pocket that's been identified by Pocket Finder. And what we find is that 7 out of 10 of the final orientations fit well with the actual crystal structure. So we're seeing lots of different orientations here. This is the crystal structure here. None of them is absolutely perfect, but they're all pretty close. And 3 of them really fit very well into the NADPH binding site of DHFR. That brings us to the end of part 2, and in part 3 we'll look at virtual screening, de novo design, improving lead molecules and some examples.